We're starting chapter 17. We're going to be talking about what makes reactions go, not just what makes them go to completion, but what makes them reversible as well. So we're going to start with some reminders about getting molecules colliding with each other. So we're going to review a lot of stuff from our solutions when we talked about dissolving. We're going to be talking about energy, as in endothermic and exothermic reactions. So we're going to recall a bunch of material that we've already studied this year. I want to remind you that in order for a reaction to occur, the molecules have to collide. Old bonds are going to have to break, new ones are going to have to form, and the greater the number of collisions, the greater the chances of a reaction happening. If they're not colliding, they're not reacting. To get them to react, you have to break the bonds. For all kinds of reactions, increasing the concentration will increase the rate of reaction. The more molecules there are of the solute mixed in with the solvent, the more likely they are to collide. For solids, if you increase the surface area by crushing the material and stir it, you get more molecule-molecule interactions. For solutions and liquids, if you add more of the solute, you will get more reaction. For gases, if you increase the pressure or decrease the volume, you keep the gases dissolved, which makes them available for reaction. Molecules have to collide with sufficient energy to break reactant bonds. If you increase the temperature, you increase the kinetic energy, and that affects the reaction rate greatly. Most chemical reactions take place at higher temperatures more quickly. This happens for two reasons. You get more collisions, and each collision happens with greater force, greater energy, so you're more likely to break bonds. Molecules must collide in the correct orientation so new bonds can form. So this is a brand new idea that we didn't talk about at all when we talked about dissolving. The word we're going to use for this is steric factors or steric effects. The orientation of the molecules makes a big difference. We're going to look at one example of nitrosyl bromide reacting. So here are some pictures. The first one shows the bromine-bromine interaction that will result in the correct orientation of collision that will result in the products predicted by the reaction on the previous slide. You can get the bromine and bromine to collide this way as well. So you can have a side-to-side collision or a head-on collision between those bromines. But if you don't collide the bromines, you don't get a reaction. So in this case, for this particular material, the steric effect is tremendously important. Now we're going to introduce some definitions. I'm going to give you a minute to get your pencil ready in case you haven't been writing yet. This is the part you'll need to get down for definitions. The first one, activation energy, EA. That's the minimum energy of collision needed to make a reaction happen. The bigger the activation energy, the slower the reaction. The bigger the hill you have to climb to get the reaction started. It's greatly affected by the temperature and the steric factor. The more important the steric factor is, probably the higher the activation energy is going to be. There's another word, activated complex or transition state. That's the arrangement of atoms at the top of the energy barrier. Activated complex. That means you've got molecules colliding and they're in this snapshot moment where they're breaking and reforming bonds at the same time. That's also called a transition state. You can picture molecule-molecule colliding, breaking, forming new bonds before they fall into these new molecules. It's a very, very momentary state. Energy profiles are the graphs we're going to do with potential energy versus reaction coordinate. These illustrate the progress of the reaction in terms of energy of reactants, products, and activated complex. So let's take a look at some energy profiles and talk about these vocabulary words in that context. Here we have a picture. This picture is a graph. It's not a numerical graph, it's a qualitative graph. What I want you to notice is on the left side we have the reactants, on the right side we have the products. We have the bromine nitrosyl and the bromine on the left, or on the right, the diatomic bromine and the nitrogen oxide on the right side as reactants. The BRNO on the left as a reactant is higher with respect to the energy, which is the y-axis, than the products are. This ends up with lower energy than it started with. From left to right, just looking at the absolute value of the left side and the right side, we can see that the right side is higher than the left side is higher than the right side. What we have is this bump right here. This bump on this graph is where we will see what we call the activated complex or the transitional setting. So what we're going to do is add energy to these materials. We got energy here. And as we add energy, they start to collide faster and with the correct orientation. And then we get to this activated complex. And when that happens, then they fall down to the new energy level for the products. In this case, it's exothermic. So adding the word activated complex to our diagram lets us see that that's where we have the molecules colliding at the right speed with the right orientation. This is showing the diagram of the bromines interacting in the transition state at the highest part of this graph. Now we're going to put some numbers or talk about value differences on the graph. So when we go from our reactants to the activated complex, we have an energy change from here to here that we call the activation energy, EA. Now we're going to look at the difference between our reactants and our products. This is an old idea. That's our heat of reaction. We don't need to include the activation energy when we talk just about the heat of reaction, because the heat of reaction is the absolute value difference between the energy to form the reactants and the energy to form the products. So remember, this will be our activation energy, this will be our heat of reaction. And in this case, our heat of reaction is letting us know that we end up with less energy at the end. This gave off energy. This is an exothermic process. Catalysts have a special role in a lot of chemical reactions, including biological reactions. Catalysts speed up a reaction without being used up in the reaction. A special case of catalysts are enzymes. They're biological catalysts. We have two labels to talk about catalysts. We can talk about homogeneous or homogeneous catalysts. They're in the same phase as the reactants. So you put a liquid catalyst into a liquid situation. Heterogeneous or heterogeneous catalysts are a different phase as the reactants, like a solid surface that a reaction can take place on. Catalytic converters in cars are heterogeneous because they're solid state. Catalysts allow reactions to proceed by a different mechanism, a new pathway. It predominantly affects the steric factor and makes it easier for substances to collide. The new pathway has a lower activation energy, so more molecules have activation energy, will have the activation energy, and the rate of reaction will increase. The presence of a catalyst doesn't change the heat of the reaction. The absolute value from here to here, this is delta H. This doesn't change by the catalyst. Catalysts are initially reactants, sort of, but then they're products too. So they don't really get used up in the reaction. So let's take a look at one of these energy diagrams that talks about a catalyst. We'll have the same energy of formation of our reactants and the same energy of reaction of our products, and the difference between them will still be delta H. That doesn't change. What does change with a catalyst is it lowers the energy needed to get to the transition state. It lowers the energy needed for the activation energy on this part. So here's a sample problem. It says, look at the graph and identify the following. So why don't you sketch one of these on a piece of paper. You're going to have potential energy of the reactants, potential energy of the products, potential energy of the activated complex, the activation energy for the forward reaction, the activation energy for the reverse reaction, which is a new idea, the activation energy for the catalyzed reaction, so you'll just sketch in a new line, and the delta H. If you go from left to right, is it exothermic or endothermic? I'm going to give you a minute to work on that. And then I'm just going to start drawing lines from these definitions to their places on the graph. Activation energy forward. Oops, didn't quite pick up. Activation energy, if it was to go backwards, it would have to overgo this hump here. let's see, activation energy was catalyzed. Let's make a new line. There's a catalyst, and the activation energy will be from here to here. And delta H. Delta H is the absolute value of the difference of what you started with and where you ended. So this is delta H. So this starts lower and ends higher, which means you have to put energy in. So it's endothermic. Okay, that's it. Let me know if you have questions.